Good evening, everyone. Um, this is our 10th interactive session for the course Soil Mechanics 1. And my name is Saida Said, and I am one of the TAs for this course. So, in the week 10, we have studied Earth's retaining structures. Okay, and lateral earth pressures. And these, in the week 10, we have seen some questions on cohesionless soil. While cohesive soil has been covered in week 11, so we will be doing some questions today on uh, these topics for cohesionless soil. And since it's not a very long topic, I will be starting with a little some basics of uh, this lateral earth pressure theory. So some of the things that you should understand is, see, when you study hydrostatics, you do that first law of hydrostatic law you study, in which you say that at any point in uh, a body of water, the forces or stresses from each direction are the same. Okay, this is the hydrostatic law in which you will experience the same force, same stress from each direction. If this is the depth at which, one second, if this is the depth at which, uh, okay, the point you are considering is taken, it is at Z, and gamma W is the bulk weight of water, then this stress will be gamma W times Z. And in material of the direction, it will be same from all directions. But you see, water and soil are very different. Water is a homogeneous material, it's an isotropic material. However, soil is not an isotropic material, it's not a homogeneous material, especially it's not isotropic. So in soils, when we have a point at a depth, we know the vertical stress will be gamma bulk of soil times Z. But what will be the lateral stress here? This will not be equal to gamma times Z. It is in proportion to the vertical stress, and we can say that sigma horizontal is directly proportional to sigma vertical, or we can to say that sigma horizontal is equivalent to k times sigma vertical, where k is a constant of proportionality. And this constant, the value of this constant will depend on the state of your state of stress that the soil is in. Is it in active stress, passive stress? Is it at rest? So that is what we will basically be studying in this topic. That is the first point for you to visualize it easily, the lateral stress at a point. Okay. Now the second point is, so when we talk about two things in retaining structures. One, we talk about the stress on retaining structure, and we talk about failure mode of soil behind the retaining structure. So why this is important is you have to understand that until now, whatever you have been studying, the soil was, say, like in strength of materials, you draw a sigma, a stress strain curve. You draw a stress strain curve. Okay. So in let us say, for example, you study in your steel, you have this kind of a curve. You have a yield point here, and you say that the soil is elastic in this region and it is plastic in this region, and the stress has surpassed, for the plastic region, the stress has surpassed this yield point. Same goes with soil. Soil is basically a non-linear elastoplastic material. Okay, so you have a stress strain curve, something like this. Okay, and there is this short range up small, this is quite small, this strain, up till which you will have elastic behavior, and after this you have the plastic behavior up till here. We There are many theories for the uh, behavior of soil, but we can talk about more fundamental theories or more easy, like simpler theories, because this is an advanced topic. So we believe that we idealize the soil to be elastic, perfectly plastic. So it will have an elastic behavior at very small strain, after which it will show a perfectly plastic behavior. By this perfectly plastic behavior, we mean that there is large amount of uh, strains. Like the stress is not increasing, but the strains are increasing. So that is the typical definition of plasticity. Definition of plasticity is that you see no increment in stress with increment in strain. You say that the material has reached its plastic limit. So why I am mentioning this is because when we talk about the soils in retaining walls, behind retaining structures, and we say that there has been a slip. See, this failure, even after plastic, this failure has occurred, which means that this portion of soil which has detached from the main soil mass is in plastic failure. And whatever we studied about shear strength, we draw this Mohr-Coulomb circle. Any soil state below this circle is an elastic soil state. If I take a soil state here, 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 these are all elastic soil states because as soon as it touches this failure surface, this is a limiting state. And you should know that this kind of soil state is not admissible. Okay, so basically, what happens is what happens is if this is your failure surface and you are loading your material, let us say that you are loading your material in a drained condition, the stress paths, let's not talk about stress path, but let me say the Mohr-Coulomb circle will be something like this, and you will get, as soon as you reach this surface, which is called the yield surface, and in case of Mohr-Coulomb surface, it is in the Mohr-Coulomb failure criteria, it is this surface. This is phi and this is c. As soon as you reach here, your stress reaches here. So as soon as you reach this point, you can say that your soil has failed. So in earth retaining structures, what we assume firstly that soil is in plastic failure. Obviously, not the soil which has not failed, but any failure in earth behind earth retaining structure of soil is plastic failure. So basically, there are these theories of limit analysis of plasticity that help us to determine the failure load and failure criteria for earth retaining structure. We first assume that the soil behind the structure is in plastic state. Then we can draw in the uh, Mohr-Coulomb failure envelope. We can say that if this is in failure and we know like the failure line, the failure stress will be on this line. So if you have a stress condition like this, you will have the sigma 1 and sigma 3. And you have this as 2 theta. This is the phi. So you learn about active and passive earth pressure. Active earth pressure is when your wall moves away from the backfill such that some of the pressures are released. That is the sigma x decreases. And passive of pressure is when wall is moving towards the backfill and sigma x is increasing. So Rankine gave a theory. Oh, and the other fact is that okay, that is about okay. The third point that I would like to discuss is that we perform this analysis in plane strain condition, assuming a plane strain condition. So, what exactly is plane strain condition? So, uh, when you're doing these kind of analysis, in real life, in real world, we have three dimensions: x, y, z. For ease of calculations, there are many problems that is not necessary that we uh, formulate the problems in all the three dimensions. There are some cases and some simplifications we can make to make the calculations easy. So, from three dimensions, we can reduce to two dimensions. But how and when? For example, I have an embankment. This is the cross section of the embankment. And let us say that it is very, very long. Obviously, it's not of infinite length, but this length is much longer than the x and y lengths. Okay, so what will be the strain in x direction will be the dx over original length in x, epsilon y will be dy over original y, and epsilon z will be dz over original z. You see, original z is too long. This is going to be a very, very, very small number. So in this case, what we do is when we have this kind of a situation where we have a wall or we have an embankment, any kind of problem in which the cross section is very small as compared to the length, we take the epsilon z, which is the strain in the z direction, as 0. And from elasticity theory, we can say that sigma x is equivalent to, sorry, yeah, epsilon x is equivalent to sigma x by e minus mu times sigma y by e minus mu times sigma z by e. And same is for epsilon z, same is for epsilon y. So, see, we have a relation between all three stresses. Okay, so sigma zz we can calculate from this relation. We don't need to explicitly calculate sigma zz. I should have mentioned earlier that in any problem, for example, you are taking the triaxial sample, you are taking the vertical direction, you are taking the horizontal direction, and you are assuming that the intermediate stresses are equal to the horizontal direction. Even in your direct shear test, you are taking the cross section, isn't it? So you are taking the vertical direction and you are shearing in this direction. You are not considering the third direction. But basically, because we have three dimensions, we have sigma x. This you must have studied in your strength of materials course. You also have a tau xy, tau yz, mm, tau xz, tau yz, and this is a symmetric matrix. So these are the stresses that we need to know, and the strains are again the epsilon zz, gamma xy, gamma xz, gamma yz. So these are the stresses and strains. But in plane strain condition, as I mentioned, we take this as 0 and we correlate sigma xx and sigma yy to get sigma zz. So basically, what we are doing in plane strain condition is we are taking, and because this is taken 0, gamma yz and gamma xz also becomes 0 because in that direction only we are not taking any strain. So the only things we need to evaluate become sigma xx, sigma yy, and tau xy. And that is what we do when we are talking about Mohr-Coulomb and all these shear strength. These are the components that we evaluate because we are taking a plane strain condition. Other thing that we can take is which is usually not very relevant in soil mechanics, but more relevant to structural analysis. Sometimes you have a body that has a very small depth as compared to the cross section. For example, if we talk about a cantilever, cantilever is not just this. Cantilever extends in this direction. Okay, so if you see this cantilever, we are loading here, isn't it? We're loading in this uh, and we are loading in this plane, but as compared to the depth in the third direction, consider like a piece of paper, it will have no stresses in this direction because the area is too small, isn't it? Okay, so we take sigma z as 0 and this becomes our plane stress case. So for thin structures that have small lateral cross section and other forces are in this plane, in this xy plane, we are taking the forces, not in the z plane. So, excuse me. What we do is we take plane stress case. This also reduces our analysis from three dimensions to two dimensions, and that is what we are doing. In fact, in our dams, in our retaining walls, in even our strip footings, our not isolated footings, but when we have strip footings below a wall, we take a plane strain case. When we have an embankment, we take a plane strain case. Um, we have a retaining wall, we take a plane strain case. Okay, so that is much appreciated in um, geotechnical engineering. So that was the third point. The first point was to understand that in retaining structures, we are talking about plastic failure. What we do is we define the surface, the condition of failure, and then we calculate sigma 1, sigma 3. We're not concerned with, we are more concerned with the state of failure than the current stress. Okay, anything else? I think that is it about the discussion. Now let us try and solve a question um, of retaining walls. So determine the magnitude of the resultant. Okay. One more thing that I wanted to mention was, so what is the main difference between Rankine's theory and Coulomb's theory? You see, Rankine's theory was given for smooth walls and Coulomb's theory for rough walls. Now, why it is important is because smooth walls will not have any friction along this interface, while rough walls will have a friction. So the resultant that will cross this will be 90-degree in Rankine's method, while in Coulomb's method it will be at an angle equal to the friction angle between the wall and the soil. So that is the difference between Coulomb's and Rankine's theory. I know we start studying about uh, horizontal wall, vertical inclined backfill, inclined back of soil, and out of all these conditions, we forget the basic thing. The basic thing is that this is a rough back, and thus it will have a inclination. The resultant will have an inclination to the wall, while in Rankine's theory we have a smooth wall and it will not have an inclination. Okay, so let us move on and try to solve this question. Determine, let me increase this a bit. Determine the magnitude of the resultant at rest force per unit length of the wall. See why it is talking about per unit length. As I mentioned, we assume that this in this direction the length is very long. So we take a unit length along the perpendicular to the two axes that we are taking in plane. Okay, so we will take a unit length, because when we calculate the force or load due to the soil self weight, the weight will be height into length into breadth, but length we are taking length we are taking here as 1. So that is why you have to mention that it is the strength per meter, not of the entire wall. Okay, determine the magnitude of resultant force at rest per unit length on the wall. And we have been given that there is a clay layer up to 2 meters, and then there is a sand layer up to 6 meters. And we have been given the properties of sand as well as clay. So let's try to solve this question. So for sand, phi is 34, and you know K naught we can write as 1 minus sine phi, which is Jacobi's equation. There is one more equation that has been given, which is K naught for sands is equivalent to 1 minus sine phi into OCR, which is the over consolidation ratio, raised to power sine phi. Let us go with this. Let us forget about this for now, and we will have 1 minus sine 34. Let's calculate. Which is 0.44, and from the other equation that I mentioned, we get a K naught value equal to 0.65. Let's move ahead with this because of the reference that I have taken. Otherwise, this is perfectly all right. K naught is 1 minus sine phi. Okay. So the reference is also used an equation for K naught for clays, but let us not delve into too many equations, and I will just give you the K naught for clay. Nine, two, two. And in these questions, firstly we will calculate the sigma z. As I mentioned, the sigma h is proportional to sigma z. So first let's calculate sigma z. Groundwater is here. This is a dry soil. This will go like this. This will be gamma z, which is 18 into 4. And then we will have gamma saturated is 19. So we will have up till here. This will be 19 into 2, and the core water pressure will be 2 into 9.81. Okay. So at Z, equals, let's take z from here, 0, we know. So for here, we will be using k gamma. So the horizontal will be k naught sand into gamma h into this vertical stuff, and this will be k naught clay into gamma h2. Let's call this h1. Magnitude of the resultant at rest force. Okay, so we will have a this diagram. This will be 18 into 4 into k naught. So you see, we'll have a very interesting thing here. Let me show you. Excuse me. Okay, let's start from here. Okay, so at z is equivalent to 0, obviously, we will have sigma equal to 0. At z is equivalent to 4, due to the upper part, we will have k naught sand into 18 into 4. 18 into 4 is the like pressure here, and here we will have lateral pressure as k naught into 18 into 4, which is 0.65 into 18 into 4, which will be 0.65 into 18 into 4, 46.8. Okay, and the variation will again be triangular because it depends on the overburden pressure. But at the same time, at z is equal to 0 for the lower layer, we for the lower layer also we have this stress here, but the K naught is different. So we will have a K naught K into 18 into 4, which will be 0.9, or how much was it? 922. 922 into 18 into 4. Okay, so we will have 0.922 into 18 into 4, which will be 66.38. So we will have something like this. This will be 66.38. This will be 46.8. And now if we talk about the pressure here, how much is the pressure? At Z is equivalent to 6 meter, sigma vertical is equivalent to 18 into 4 plus 2 into 19. Remember that we only use effective stress values for calculating this. So, because if you know that the water will have same pressure in all directions, and uh, it will not uh, contribute to a vertical stress being net horizontal stress being uh, evaluated here. So will be 19 minus 9.81, and sigma h will be K naught K into this much is 18 into 4 plus 2 into 19 minus 9.81, 90.38 into 0.92, which is 83.33. It is something like 83.33. And if you talk about the pore water pressure, the pore water pressure will be below the groundwater table. It will be equivalent to 9.81 into 2, 19.62. So what happens is, as I mentioned, that the water will have a stress in all directions. If you take any surface here, you see the latent pressure that will develop will be due to only the soil, not the water, because since it is same in all directions, the net effect of the water in the lateral direction is zero. In any direction is zero. So that is why it's called a neutral um, force. So we will not be in our calculations. We only take sigma dash, which is the effective stress. Okay. So this was about the magnitude of the resultant. So what will be the resultant now? This is the diagram. To calculate the resultant, we have to calculate, we will divide this into smaller shapes. Maybe I should have done this. Okay, so this will be P1, P2, P3. Okay, uh, let me draw this again. Okay. This was 46.8. This was 66.38, and this was 88.33. So we will have a triangle of height 4, then we will have a rectangle of height 2, and the width will be 66.38, and then we have this will be 66.38 minus 88.33 minus 66.38. This will be 21.95, and this will be 2, and this will be 46.8. This will be at 4 by 3. This will be at 2 by 2. This will be at 2 by 3. Okay, let's calculate. Let's call this 1, 2, and 3. So region 1, 2, and 3. So we will have height is 4, 2, 2. Breadth 46.8, 66.38, 21.95. Area half of BH, BH, half of BH, which will be 93.6. This will be 132.76, and this will be 21.95. And let us take the x bar from datum. Let the datum be this. Okay, so x bar will be 2 plus 4 by 3. Here it will be 1. Here it will be 2 by 3. So if I sum this, the total force is 93.6 plus 132.76 plus 21.95, 248.31. So the R is 248.31, and it is acting at, we can write R times x bar is equivalent to A1 x1 bar plus A2 x2 bar plus A3 x3 bar. So R times x bar is, we multiply these columns, 93.6 into plus 132.76 plus 21.95 into 2 by 3. So this is 459, and our x bar will be 459.39/R, which is 248.31. 1.85 meters. So our x bar is 1.85 meters. So on our wall, if this here will be our resulting force acting. Okay. We have to add the, because we are taking the total load, so we have to add the load due to U dash. So due to the pore water pressure. Due to the pore water pressure, this will be, this is 19.62. Let's add another column here. U, height is 2, V is 19.62. Is it? Yeah. So this will be 19.62. Half pH is equal to 19.62. I have to add it to this 248.31. 19.62. So we will have a total force of 67.93, and we will have uh, another area here. See, don't get confused. I said that we don't take the effect of water in this diagram. Why? Because when we are taking this vertical direct vertical stress, then we are multiplying with our K naught, isn't it? But water you have to take separately, because you cannot multiply. If you, in your dam engineering you have studied that water will on an embankment will have gamma h. It will have the load in the horizontal direction because of the hydrostatic pressure. But in soil we have K times sigma h, or sigma vertical. If we take the sigma vertical as total load, we will be multiplying even the gamma w, even the pore water pressure with a factor of K, which is not correct. You understand? That is why we don't take it with the total pressure, because if we take total pressure here, we will be multiplying the U component with the earth pressure coefficient. So we have to consider the water pressure. I'm not saying that we don't consider the water pressure. We don't consider it in the lateral pressure. We have to calculate it separately. So actually, let me correct this. Um, this will be 93.6 into plus 4/3 plus 132.76 plus 21.95 into 2 by 3 plus 19.62 into 2 by 3. This should be 472.47. And your x bar will be 472.47 over 267.93, which will be 1.76 on the bottom. Okay, if you see here, even though the sand has more height, the resultant first of all will be in the bottom third because of the triangular distribution, and secondly there is also groundwater table in the lower part, and the uh, OC, the K naught for the clay is greater than the sand. That is why the resultant has actually shifted downwards. So we have a resultant at 1.76 meters. Okay, so that was the first question. Let us try to solve another question for sands. Okay, so this is a 6 meter high retaining wall, and we need to calculate the runtime active and passive forces per unit length of the wall, also the location of the resultants. Okay, so for active and passive pressure, we know since C equals 0, we will have Ka equal 1 minus sine phi over 1 plus sine phi, and we will have a Kp of 1 plus sine phi over 1 minus sine phi, which will basically be 1 by Ka. Okay, so let's calculate. Phi is 36, so 1 minus sine of 36, 1 plus sine of 36. Approximately approximately 0.26, and if we invert it, we will get 2.85. So let's calculate the sigma vertical for this. Actually, let me go out there only. So we have This will be 16 into 6 sigma vertical if we talk. Active will be 16 into 6 into 0.26. Passive will be 16 into 6 into 3.85. See, this will be only the height. For the total load, we have to calculate the area of this triangle. This is 24.96. This will be 369.23. So our PA will be half of base 24.96 into 6, and our passive pressure half of base 369.23 into 6. This will be 80.88 kilonewton meter per meter. This will be 369.83 into 6.3. 1107.7 per meter, I think. Okay, yeah. Kilonewton per meter square per meter is basically kilonewton per meter. Okay, and what will be where this pressure will be acting? See, the height of both the triangles for active as well as passive is same, so both will be acting at h by 3, which is 6 by 3, which is 2 meters from the bottom. Okay, which is 74.88. I can mistake. This is 107.7. Okay, so that I think is clear. Um, Let me show one more question for today, and there is not much to be discussed about it, so that will be the last question for today. And hopefully, after that, let's meet next week where we will discuss some questions on the clay soils and hopefully some slope stability questions. Okay. So we have to determine the Rankine's active and passive pressure for this soil and also the result. Okay, so we have been given 5 dash 30, 5 dash 35. Both are sands, but there is a little bit of difference in the denseness. So let's go for active phase for initially. So we will have a Ka1 equals 1 minus sine of 30 over 1 plus sine 30, and we will have a Ka2 equals 1 minus sine 35 over 1 plus sine 35. 1 minus sine 30 will be divided by 1 plus sine 30. This will be 0.33, and this will be 0.27. Okay, both are 3 meters. Here we have groundwater. So let's take gamma W is equal to 10. So our gamma submerged will be 8 kilonewton per meter cube. And let's calculate the vertical stresses. First, sigma vertical, this will be 3 meter, 3 meter. And this will be 3 into 16. And then we will have let this be 8, 3 into 8, and let this be 4 water. This will be 10 into 3. Okay, now let us talk about the sigma horizontal. So the stress here will be 16 into 3. See, this is 48. This is 24. And this is 30. Okay. And initially K is 0.33. So we will have up till here, this will be 48 into 0.33. But at the same time, we have this interface, and at this interface, we will also have due to soil to 48 into 0.27, and then it will increase, and this will be 24 into 0.27. Okay, so and we will also have a pore water pressure. This will be 10 into 3. Okay, now let's calculate. How do I calculate? Let's calculate it. How should I say? Element wise. Okay, let's take it here. Okay, okay. So we have 1, 2, 3, and also 4. Okay, body 1, 2, 3, and 4. So we will have a height. This is 3, this is 3, this is 3, and this is 3. And we have breadth. This is 48 into 0.33. 15.84. Okay. For the body 2, it is 48 into 0.27. 12.96. For body 3, it is 24 into 0.27. 6.48, and for body 4 it is 3 into 1030. Okay, and what will be the area? This is half pH, this is pH, this is half pH, this is half pH. So the P for each will be 15.84 into 3 by 2. This is 23.76 of this into 12.96. 19.44 half of base into altitude. 9.72. And 45. Now let's see the X bar for these. X bar for 1 is, this is 3, and this 3 by 3. 3 plus 3 by 3. This will be 3 by 2. This will be 3 by 3. And this will be 3 by 3. Okay. So the total load in active case is 23.76 plus 19.44 plus 9.72 plus 45, 97.92. And it will be acting at summation of PAXA over summation of PAI. So this will be 23.76 into 4 plus 19.44 into 3 by 2 plus 9.72 into 3 by 2 plus 45. This will be 183.78 over 97.29. It should be 1.89 meters from the bottom. That is where the resultant will be acting, and the resultant is this much. And if we talk about passive force now, all we have to do is replace these values with the passive values. So let's try to do that. So what was the K passive that we calculated? We did not. Let's calculate K passive 30 and 35. No? Yeah. Let's calculate K passive. It will just be, we have calculated 0.33 and 0.27. So Kp1 will be 1 by 0.33 and Kp2 will be 1 by 0.27. So it will be 3 and this will be 35. Yeah, 3.69. So here we multiply by 3 and here we multiply by 3.69. 3.69. Okay. Let me take this to. Okay. So this will be same. This will be different. And this will be different. So this is 48 into 3, which will be 144. And at the bottom it will be 48 into 3.69, which will be 177.12. And then at the bottom we will have 24 into 3.69, which will be 88.56. And here we will have same water The area will be 216, 177.12, 177.12 into 3. This will be 531. Did I do half of it here? 12.96 into 3. Okay, I made a mistake here. This is 38.88. I calculated for triangle. This is 117. This is 23.76 into 4 plus 38.88 into 3 by 2 plus 9.72 into 3 by 2 into 1 plus this is 208.08. So 1.76. Okay. And we will have 88.56 into 3 by 2. This is 132.84. This is 45. Okay. So the total force, obviously, this will be greater than our active force. This is 925.2. And if we talk about summation of Pixi bar, this will be 216 into 4 plus 531.36 into 3 by 2 plus 132.84 plus 47. 1838.88. 925.4. This is 1.98 meters. And if you draw the diagram for the passive pressure, you will see that in earlier you had a kink inside, you will have a kink outside here because this is 216. But now you will have a passive pressure like this. Okay, so that is it for today, guys. Thank you very much. Let's meet next week.